One of the simplest toy models that I teach about at Iliad are deep linear networks. So these are linear networks which have depth, they are deep, so they have multiple layers. But the activation function are all the identity. There's no nonlinearity, so they are very limited in their expressivity. They only learn linear function. But they have, in fact, already quite complex and intricate loss landscape and dynamics. It makes it easier because the nonlinearity is cursed to study mathematically, and linearities is great because we can do linear algebra. We can just do a lot of math when things are linear. There are two different kind of analysis you can do. One is a static analysis where you try to understand the loss landscape of the deep linear networks, and in fact, the loss landscape has already some of the complexity that we can find in the loss landscape of nonlinear neural network. So the loss landscape in parameter space is non-convex, and they have global minima, and they have saddle points as well. And mathematically, we can show also that they don't have any spurious local minima, meaning that all the critical points, all the points at which the gradient of the loss is zero, are either global minima or saddle points. Yeah, and you can study the geometry of the loss landscape, the symmetries of the deep linear networks. They have a lot of internal symmetries. They are symmetric. You can rotate the weights. You can rescale them, and the function is invariant under all of these symmetries. Then you can try to think about, let's try to quotient out all of these symmetries and simplify a lot the loss landscape. Yeah, there's a lot of rich math behind this, representation theory, algebraic geometry, and you are only looking at the geometry. We have not even done any dynamics yet. One particular interesting aspect of studying the learning dynamics of deep linear networks is that you can understand how does initialization and depth affect training. Typically, if you initialize your weight with a large variance, you are what people call sometimes the lazy regime or the NTK regime, which essentially is a regime that is linear, when the training dynamics is completely linear, meaning gradient descent in function space is an ordinary linear differential equation. Your NTK, your neural tangent kernel, is frozen at initialization, and things behave you basically essentially you've already have the direction of the feature, and you're just doing a regression over them. That's the lazy regime. And on the other end of the spectrum, if you initialize your weight with a very small variance, a small variance around zero, then the training dynamics is in what people call the saddle-to-saddle regime, or the feature learning regime, or the rich regime. This is the most interesting regime in some sense, because that's where we see a very different behavior from just linear regression. You can learn something interesting about simplicity biases of gradient flow. One thing that you learn, for example, is let's say you are learning a teacher matrix. So you have y is equal to mx. M is some matrix with some singular values. And in the saddle-to-saddle regime, there is a particular order at which you are learning these singular values. Gradient flow, gradient descent, is going to first learn the largest singular values of the teacher matrix, and then the second largest singular value of the teacher matrix. You first learn the singular values and singular vectors that have the largest impact on explaining your data. So in some sense, you first learn the first direction that explains the most data covariance, basically. So you could stop training after learning one direction, and you're we already the direction that explain the most of the data, even though we only have learned one particular feature. In the lazy regime, you will learn all the singular values at the same time. So you see that depending on how you initialize your network, when you are at depth, you have this spectrum with two different extremes. Well, one extreme is lazy linear regime, and the other extreme is this saddle-to-saddle feature learning regime. In fact, you can see example of the saddle-to-saddle, or similar to the saddle-to-saddle regime in nonlinear neural network, transformer with attention only. There's some recent work by Andrew Sachs who showed that we can have this sort of a saddle-to-saddle-like regime in more complicated nonlinear models. I think the hope is we can increase the complexity of the models that we're using. I think we have a decent amount of understanding of deep linear networks. And the idea would be now let's move on to more complicated toy model. More generally, there are these polynomial neural networks where the activation function are some polynomial. For example, quadratic, just only quadratic activation function. They are related to tensor networks, which are a product of tensors. And this tensor network, they are multilinear in their data and nonlinear in parameters. There is some notion of singular value decomposition, some notion of rank. So we have a lot of the tools from linear algebra that we use in deep linear networks that we can also use on this tensor network, although this tensor network, they can learn nonlinear functions. And now we have a sense like what are the interesting questions in deep linear networks? Can we find similar phenomena in this tensor network? Can we import a lot of the results from deep linear networks to this more complicated tensor network? Building our way up to learning non-linear function with some hierarchical structure. Can we develop a mathematical understanding of that with good toy models? That is one perspective that I'm quite excited about personally.